So we're going to be taking a look at number 79. This is a great problem because at first it looks like it's going to be really hard, and it turns out to be not so bad. So what we have here is a wheel of mass m with a radius of r. And now that wheel of mass m needs to climb the step against which it rests. And to do that, we're going to put a horizontal force F on the axle. What minimum force is needed? And what we're told is that the step has a height of h. So our first thought is, I have no idea. And it looks like you did not get much beyond that first thought, although you do have a little bit of thing going on there. So tell us what you have.
Well, just the sum of forces is and is at least in the x direction.
So sum of forces in the x direction should equal what?
F5.
Okay. That should equal then applying Newton's law. Yeah, maximum acceleration. Good. Now he claims that there's only one force acting. And I claim that's impossible.
Because the step is
Right. And so at that point, we recognize that a fundamental thing, a fundamental problem-solving technique that we talked about didn't happen here. What was that fundamental problem-solving technique? Free body diagram. That's right. So we needed a copy of this so that we could label all of the forces acting. And only one of those forces is acting. What other forces are acting? From where? What it's resting on, sure.
There are no more forces from the other side.
Ah, good. There's going to be another normal force. Which way is it going to point?
Opposing or the opposite of the surface. So
Yeah, it's going to be pointing in this direction. FN2. Good. Okay. Any other forces? Good question. Where's that friction coming from? On which surface here? The bottom surface? Which way will it point? To the left. And grab, pulling straight. Okay. Now, our first thought when we look at this is that's a heck of a lot of forces, and that's a lot of unknowns. I count 1, 2, 3, 4 unknowns, including the F that I'm supposed to be looking for. So there must be something about this problem that simplifies the situation. Let's think carefully. If I am pushing with this force right here, think about it physically, and I am raising the wheel off of the bottom step, what will the value of the normal force be with that bottom step? It's going to be 0. Right at the moment where I lift up off the bottom step, there's going to be no more pressure. There's going to be no more force, excuse me, use the wrong term. No more force.
Except then what cancels out energy?
Ah, good question. So that's going to be 0. And since the normal force is 0, the frictional force is automatically 0 because the frictional force is caused by, indirectly, by that normal force. Yeah. It's a normal force. It's the force of contact between the corner of the step and the wheel, Alexis.
So what if it's only rotating on one point, there's nothing friction there?
Yeah,
Okay.
that's great. Or if there is friction there, it will simply serve to keep the wheel from unslipping down.
Okay.
Yeah, that's a great point. So Mac asks a fascinating question. How do I now understand these forces? Well, like this, basically. except that I need to modify my actual sum of forces. Yeah,
How's the bottom up and zero?
because as I am lifting up off that bottom step, I'm not in contact anymore.
Oh,
So right at the moment where we lift off, the normal force is zero.
Question.
Mhm.
It's being pushed horizontally, so the rest of the normal force would be instead on the upper step. When the normal force just be shifted instead of.
Exactly. That's what this Fn2 is.
then we have to do like the sign per sign.
Yeah, and you'll have to break up that into some just components.
That seems painful,
But yeah.
and it seems painful because we don't really know what the angle is. And there's no indication in the problem of what that angle is.
So is there something else we do besides forces?
Maybe we can figure out what the angle is, but that seems very painful to me.
So like right here.
Is there something else we do besides forces?
There is something else that we could do besides forces. What is it? Something we could do sum of torques. So we could do sum of torques about which point?
That point, the blue
The
dot.
point of contact?
Possibly the point of contact. That's actually going to be a challenging problem that we don't have. Well, we might be able to do this. Let's try about the blue dot. That kind of makes sense. I can see how to do the torques about the blue dot the easiest. On the other hand, the center, about the center, would at least allow us to do moment of inertia about the center, which we know how to do. We don't know how to do the moment of inertia of the wheel about a point on the edge. Yeah. We may or may not need to. Let's call that moment of inertia I. And let's do some of the torques about point P. Okay. So let's see here. What forces are acting to give us torques? Well, there are three forces on the free body diagram. One of them, the normal force, is going directly through point P. So its moment arm distance is 0. The second one is the horizontal force F. And that horizontal force F is acting through a moment arm distance. Here's where it's really helpful to think about moment arm distances. Because force F is this way, and the moment arm distance is the distance that is perpendicular to it. That distance is this guy right here. Everybody see that? In other words, the actual distance is the radius r, but the moment arm distance that we're talking about that is perpendicular to it is that distance right there. What is this value in terms of the constants that we have? Well, x isn't one of the constants that we have. So force is being applied at the center of the circle. And the point of rotation that we're considering is point P. So the actual distance is the radius of the circle, but the moment arm distance, the distance that is perpendicular, the component of distance that is perpendicular to the force, is this distance right here. What is that distance in terms of the diagram, the quantities in the diagram?
I guess it would be half of
It kind of looks like it's half of r,
but
but it might not be exactly half. What would it depend upon? Yeah? It would depend upon the angle, and what about this? What about the quantities that you see right here is going to change that angle?
wait, is
We're looking for the blue distance in terms of the quantities that we have. We only have two distances in this problem. What are they?
H,
H and R, right?
but we can't like
So where does R stretch from? From the center down to here. Where does H stretch from?
Oh, so,
Yes! It is R minus H! Exactly.
wow.
This distance is R minus H because it is the radius, take away the height, H.
That makes sense.
And finally, this force is causing a clockwise rotation about point P. So we can say that F times R minus H is a negative torque. Now this is the part that's a little weird. We're going to have to think about this. The other force that we have is mg. It's clearly causing a counterclockwise rotation, so its torque is going to be positive. But now we need to get its moment arm distance. And the moment arm distance is going to be the distance that is perpendicular to that force as it pulls through. It's that distance right there. So I need to somehow come up with a formula for that distance. Can anybody see a nice geometric way to get the red distance here?
So transverse.
There is. Can we mark up any distances here? Mm-hmm. Yep, he sees a triangle. I'll let other people get a chance to catch up to you. One of the basic things that you should do when solving a problem is to do a geometry markup. So the geometry markup, we're going to go through and label as many of these things as we can. So for example, I can label this guy as what? R, because it is the radius of the circle. And I can label this guy right here as R minus H, because we already found that it was R minus H. And while I'm at it, I can label this guy right here as H, because it's the same right there. Okay? And we're looking for the one in red. So now Justin sees the magic tool of analysis. He sees a right triangle with Pythagorean theorem. That's exactly right. Everybody see that right triangle? Use the Pythagorean theorem to find out what the side of that triangle is. Go. Your answer will be in terms of R and H. Mm-hmm. If we extract that right triangle right here into the diagram that we're looking for, this is side x. We can say that r squared equals r minus h squared plus x squared. Let me go ahead and simplify. Because that allows me to cancel the r squareds right here. And I get this interesting relationship that x squared is equal to all of this, and x is the square root of that right there. Huh, it's a little ugly, but it is what it is. And so I'm not too terribly intimidated by it. This is the distance that I needed. And that gives me the torques exerted by each one of these three things about point P. And because I am exerting the minimum force, therefore that is going to be the force at which the angular acceleration about point P is equal to 0. And although it's a little bit ugly, we nevertheless see that this is exactly what we need to solve for f. It's a matter of subtracting from both sides, dividing both sides by negative r minus h. Yeah.
Why is it equal to 0?
I'm trying to exert the...
I'm trying to find it.
Yeah, the middle radius. Yeah. What's that?
That's fine.
Now, we get an interesting algebra kind of thing going on here. Actually, it's not so bad. Oh, need a little more space. So, I'm going to take all this and put it over here.
I wonder if that's the formula for this one test for this.
I do like this problem.
We don't.
Well, I think what you don't like about it is, first of all, that you had to work in terms of symbols. Right. I think the second thing that you didn't like about it was that you didn't necessarily have the insight that doing sum of torques about point P was a good idea. But now that you've seen those two things, that we can work this in symbols as easily as we can anything else, and that doing sum of torques about a point is okay. All right, I guess I should have seen that probably. And the third thing that you may not have seen is the whole idea of grabbing values from a right triangle. But that's actually a basic skill that conveys to a lot of different types of problems. And when you are in calculus next year, you're going to be using right triangles a whole lot in a wide variety of situations. Am I right, guys?
Yeah, it's fine.
Yep. So that's actually something that you probably should have picked up back in the geometry and the
I picked that up, so I think it's just the torque part.
Yep.
I think that was.
Okay. Well, then study this and make sure that you have all your questions about this line answered, because this is really where the magic happens.
Why is it equal to 0?
Because we are trying to exert the minimum amount of force to get this guy to roll up over. So we're going to go for it with basically zero angular acceleration.
Okay.
Yep.
I guess if we had taken a point from the center, we would have ended up with this answer.
Yes, but we would have had to figure out what this normal force was. And that normal force has two components. One in the x direction of negative f, and the other in the y direction of mg. And so it would have been totally doable, but a little harder to work with. Yes, ma'am? Yeah. We would have gotten the same result then. The last thing that I want to point out about this answer is that it contains within it an interesting piece of insight, which is this. What happens as the step gets higher and higher? As the step gets higher and higher, the difference between R and H gets smaller and smaller, so that the amount of force required to push this thing up over increases. And in the limiting case, in the limit, as H goes to R, the amount of force actually goes to infinity. So that if the step is higher than the radius of the wheel, as high as or higher than the radius of the wheel, it is literally impossible to push the wheelbarrow up over the step. In order to push the wheelbarrow up over the step has to be smaller than the radius of the wheel. Now, apply that to a different situation. Why do pieces of heavy machinery have such huge wheels? One answer is it helps them climb over obstacles. Because you cannot climb an obstacle that is taller than the radius of your wheel.
That's why they have monster trucks.
That's why they have monster trucks. It's not just for entertainment. Does that make sense? Cool. All right. let's take a look now at some equilibrium situations. Of course, we just did take a look at an equilibrium situation. Let's look at another one. Sure. I'd like to take a look at problem number 7 on page 247. And in this, a uniform steel beam of a mass of 940 kilograms. On it is resting half of an identical beam as shown. What is the vertical support at each end? And of course, half of it is going to be 470 kilograms. So we have this situation, and there are two vertical supports, and we better make those vertical supports a little thicker, or this whole thing is going to collapse. Because 940 kilograms, almost 1,000 kilograms, is going to be close to a ton of steel. So we have 1.5 tons of steel sitting on top of these two vertical supports. And the question now is, what is the force acting on each one? So we need to choose an object to analyze. What object makes the most sense to analyze here? We've got 4 options. We can choose the top, we can choose the middle, we can choose one of the supports. The one in the middle seems to be the fundamental one, doesn't it? Because all of those forces are going to be acting on that one in the middle. So, everybody do a free body diagram for the object, the steel beam in the middle, right there. Yep. Okay, so your free body diagram should look just like this. We have 2 normal forces coming up from the vertical supports. The weight of the middle beam is pulling straight down through its center, and the normal force from this guy must be equal to the weight that it is supporting, and it's going to come straight up through the center of that object.
So it's not facing downward, it's facing
The
normal force coming from...
oh yeah, you're right. You're absolutely right.
Okay.
It's coming downwards because the normal force. Thank you.
Yeah.
There we go. That's good. Because the normal force is exerted upwards on the other object. Action-reaction pair. Yep, I had myself all mixed up. And the way that you caught it, Alexis, is probably thinking, shouldn't this weight pull down on that beam? So you're physically feeling the free body diagram, and that's a great way to check that. Good job. Okay, so we're going to appeal now to Newton's laws. I like to start with the sum of forces. I don't always find that I need it, but I'm going to start there. The sum of forces then is going to be equal to Fn1 and Fn2 pushing up, 47 and 9400, 4700 and 9400 pulling down. And in order for this whole thing to stay resting, those forces have to add up to 0. That's going to be true about every problem in this chapter. Our forces will add up to 0, our torques will add up to 0. Yeah. Because this chapter is all about equilibrium. If I simplify this a little bit, and simplifying does help clarify the situation a little bit, then I get that Fn1 plus Fn2 is equal to, look at this, the combined weight of the two objects. So that should physically make sense to you, that these two supports are having to hold up the total weight of those objects.
Would that be negative?
No, I added to both sides.
Oh, I see.
And that would be weird if it were negative. It would mean that they are having to hold back these things as they are threatening to float off with a weight of like 1.5 tons. Yes.
How did you get from 940 to 9,000?
So keep in mind our distinction between mass and weight. Mass is 940 kilograms, so the weight is 940 G,
Okay.
which is 9,400 newtons. Good question. Now, let's do a variable count. We've got two unknowns, two variables. That makes sense because we have two supports, two unknowns here. But I only have one equation. So I'm going to need a second equation in order to be able to solve. And that second equation is going to be found by doing sum of torques about an appropriate point. Which point? Good news. There's no wrong answer. Bad news. There's really only two helpful answers. Which 2 points are the appropriate points that I could choose each support? And the reason that these are the most helpful points is that if I do sum of torques about this point or about this point, I zero out the corresponding force because its distance to that point is 0. So choosing your point of analysis or your point of rotation is the key to making your life easy or hard. So let's do our point of rotation over here at point O and see what happens. If I do the sum of torques now about point O, I'm going to march through and do one term for each force. Fn2 is at a distance of 0. This 4,700 newtons is pulling clockwise around point O. So we will take its torque to be negative. And its distance, what is its distance? Well, the only thing they tell us is that the beam itself has a length of L. And so that means that this distance is L over 2, and this distance is going to be half of that, or L over 4. Everybody with me on that? So we had to do a little bit of geometry, a little bit of geometric markup in order to get that. And while we're at it, let's complete the diagram by observing that this distance also is L over 2, and that distance right there is 3L over 4. So the geometric markup is something that we need for our torques because we need to know distances. Maya, question?
I'm just trying to read this off.
Oh, L over 4 and 3L over 4. And so the distance that we want is the distance to point O, and that's L over 4. Now for the 9,400 newtons. That distance is L over 2. Because in the picture here, first of all, the L over 2 makes sense, right? Yeah. In the problem, they tell us that this is half of a beam identical to that one. And so therefore, this distance right here should be half of that one. So L over 2, L over 4. Yeah, it's on the center. Sorry. The center of the center.
Is that L over 2?
That's L over 2. And then finally, we're ready for Fn1, and Fn1 is exerted over the whole distance L. And that is a counterclockwise torque. Good? Okay. All of these torques now have to add up to 0 in order for the object not to rotate. Yes, sir.
What was the 3L divided by 4 point?
That we did just as a matter of habit, as part of our geometric markup.
Okay.
I'll come back in just a minute and we'll pick a different point of rotation and use it. So at this point, I observe that every single term has a common factor of L, which means that I can factor it out and cancel it. So that no matter the length L, I end up with the same answer. So let me do that. I'm going to write this as L times 47 times a fourth minus 9400 times a half plus Fn is equal to 0, and the L goes away. This is negative. Yep.
And why does the L go?
I can divide both sides by L because it is not 0, and 0 divided by L is still 0. Or another way of putting it is, if you multiply two things together and get 0, one of them has to be 0, and L is not 0. So at this point, it's just a matter of adding. 4,700 divided by 4 is going to be just under 1,200, 1175. And 9,400 divided by 2 is going to be 4,700. So that when the dust settles, you get 5875 newtons for your Fn1. Now, for finding Fn2, I've got some choices. I can either come back and plug into my sum of forces right there. I like that. Let's do that. So that Fn2 is now equal to whatever this is. It's going to be a little bit over 8,000. 3, borrow, you get 83.5. Notice that Fn2 is larger than Fn1, and that physically makes sense because the half beam is over to the left, and therefore it should exert more force on the closer. Yeah, sure. I had a different option for finding Fn2. I could have done sum of torques about point P right here. And if I do sum of torques about point P, then my equation looks like this. If I do sum of torques about point P, my equation is going to be 4,700 newtons times 3L over 4 plus 9,400 newtons times L over 2 minus Fn2 times L equals 0. Notice that this is very, very similar to the previous equation except for two things. First of all, the signs on my torques have switched. Why? Because now if I'm going about point P, then the weights exert a counterclockwise torque about point P. Second thing that I want you to observe is that I used a different distance for the 4,700 newtons. Why? Because the 4,700 newtons is at a distance of 3/4 of L over. And finally, notice that although this distance is L over 2, it's the other L over 2, not this one. I'll see you tomorrow. I'm actually going to put up a video about a second problem.